this is simpler than even go-kart, with just 3 traces, which are smoke, fine dust, and coarse PM, which is mostly coarse dust. So anthropogenic emissions, biogenic emissions, or in chemistry are not included. So please note that. And here we test the direct and indirect feedback, but today, because of just limited time, I'm going to just focus on direct feedback. So how this direct feedback or aerosol radiation interaction is parameterized. In the model, by default, MERA2 climatology is used for radiation, and we add simulated smoke aerosols on top of this MERA2 climatology. So this table shows a model configuration. Let me see if this works. Yeah, this CTL means control. Basically, no feedback, only feedback from the climatological aerosols by using this FS3 HER physics suite. And the model domain is CONUS, 3 kilometer resolution, 64 layers. And another simulations that I'm going to show is this with feedback or FTB briefly, where the smoke feedback is included. So what this slide shows is smoke, the snapshot of near surface and vertically integrated smoke distributions for September 10th, 2020. Why we picked this time period? September 2020 was the most extreme fire season in the modern history of the US. And in order to check, study the impact of this extreme fire season on meteorology, we picked this season. And there are a number of challenges which are affecting the simulations of smoke during this time period. So as you see on the left or right panel, the fires were mostly in California or Oregon and also in Washington, and smoke was transported to the offshore and then was circulated back. Now, we have done rigorous verification for this case by using the AirNow PM2.5 observations. In order to show the verification, I use, which is oftentimes traditionally is used, this so-called EPA regions. So region 10, you can see on the left that map shows, and region 8, the black line is the PM2.5 average PM2.5 concentrations. In the region 10, reaching exceed 250 micrograms. So very extreme pollution events occurred during this time period. And region 8 was much lower. And here, due to the transport, basically moving smoke inland faster, sooner than what was observed, we see this underestimation, and I will come back to this later. So on this slide, what I show is aerosol optical depths, again for September 10th. This upper left panel shows NOAA 20 satellites. It's just a visible image where you can see, unfortunately, I can't use the pointer. Oh, yeah, here. So you can see all this red. It's cloudy over the ocean, but you can see all this red which shows the very high AOD values. On the right panel here, this is ECMWF aerosol analysis. And this panel shows this model AOD, but climatological aerosols only. So if you run RFS out of box or UFS in general, that's what this is the aerosol field which affects the radiation in your model. And on the right panel here, this is modeled AOD, but which includes our smoke aerosols. So as you see, these two, they look somewhat similar, and basically which shows how RFS was able to simulate AOD. And this on this slide, on the left, this radiation. This is simple, more quantitative, but preliminary verification. by using the series satellite observation for radiation. So basically what it shows is a lot of overestimation of the radiation fluxes in the control simulation because it doesn't include all these smoke aerosols. So here what we did is for September 10th again, we evaluated temperature forecast from RFS for 2 sites. We picked one, Corvallis, Oregon, here, and another is Merced, California. And these time series plots shows that by adding the feedback of smoke, we can improve the forecast 3 degrees of Celsius here, 2 degrees. And again, please know these simulations are done without data simulation. So meteorological simulation is not perfect. Full DA takes a lot of HPC time. So that's the next step. And these are more comprehensive. This is more comprehensive verification. Quite busy slide. Basically, what it shows is temperature, 2 meter temperature, 10 meter wind speed, bias, and RMSE. All these parameters are improved significantly, this blue line, by adding smoke feedback. So the key take-home message here is by just turning this smoke feedback on in this simplified aerosol modeling approach, we can improve weather forecasting skill of the model. And the RFS model, actually, the operational domain is going to be this big, this large domain, this circumferential resolution domain, which covers entire North and Central Americas. And we now, just last week, we started simulating this 2020 event on this domain. As you see, this is pretty complex, like transport patterns here, a lot of, again, recirculation, going offshore, coming back. So this is a very interesting event. And I know other modeling groups also looked at this event. So, but now this red line is RFS smoke from this North American domain. And as you can see, this is some statistics. We can improve, reduce bias on this by using this domain. So I stop here and thank you for your attention.
Thank you, Rahman. Is there a question in the room? Nothing online? Thank you. It's really nice to see this sensitivity study. If there's nothing else, I think we can move on because we have really tight schedule here. Thank you. So the next talk that we have is by Jumping Wang from EMC.
So where's the mouse I can move? What?
Okay.
This no.
Yeah, this is one.
Okay. No, not this one.
Jumping Wang, Huang.
Yes, this one.
Thank you.
Thank you.
So good afternoon, everyone. So it's a great pleasure to be here, present our work on behalf of the entire team. This is a joint effort contributed by many people from different organizations across the NOAA, including the EMC, AIO labs, like AIO, CSO, GSO, and PSO, Nestis, and our university partner. So why we care this Wi-Fi, we know Wi-Fi have a significant society impact based on a study. The total cost by Wi-Fi from the 2010 to 2019 can be rival any other critical weather events except for hurricane. And in the meantime, the Wi-Fi are the major source of air pollutant And the right figure shows increased trend of Wi-Fi burning areas. So the Wi-Fi emission become more and more important while anthropogenic keep decreasing over past 7 decades. So it's important for us to better represent Wi-Fi emission to prove the prediction of Wi-Fi impact on air quality. I don't know why it's so difficult to move forward. Oh, sorry. So to support that effort, so NOAA has developed an online CMAC system within the UFS framework. So this system actually we link the UFS-based atmosphere model with the US EPA CMAC-based chemistry model CMAC. CMAC here we treat as a Korean model. We turn off all the transport turn. So just allow the CMAC to update the concentration of chemical species at each time step, and then pass this updated concentration, the chemical concentration to the atmosphere model. So dynamic core will handle the transport of chemical species similar to the physical tracer. So to support the transition of online CMAC or UFS-EPIC from the research to operational, so we designed a single large domain to cover 3 existing operational domain, Canada, Hawaii, and Alaska. So the online system has been running in near real time since last July at the 13 kilometer resolution. We keep integrated update while we are running this system in near real time. So here I highlight some of the key options for model configuration we're using for this testing. So for instance, we use the same physics package of the GFS version 16. Another feature for this is the online system testing. We replace the current operational file product, which is the GBB-EPX, with the latest data, which is the new file product. And then nextly, just recently approved this level-based PM 2.5 emission based on our near real-time testing. They apply the scaling factor based on the scaling of this biome type, the global map of the biome type shown on the laptop. So for instance, for actual tropical forests, they applied about 4.5 to enhance the PM 2.5 prediction. Bottom right, that's the satellite detected 5 point show on this day, June 26th. We have a lot of 5 point near the Quebec Bay, Eastern Canada. And the left button is the time series comparison between the GBB-based PM 2.5 emission and our level-based emissions. So with this improvement, we see now our emissions stronger enough that will benefit our prediction. So we know we had several quite stronger fire events over the last 3 months. So here example demonstrate how model predict the fire event. So here the left panel is animation showing the evolution of model predict hourly PM 2.5 concentration compared with the air observation. So we can see this smoke generated by the wildfire transport from Eastern Canada into US and increase the PM 2.5 concentration significantly. And our model actually captured this movement of smoke and predict the PM 2.5 magnitude and the spectral pattern pretty well. Now let's zoom a snapshot comparison between the operational fault on the left and with our UFS-EPIC prediction on the right. So compare those air observation actually on the left, our operational model under-predicted significantly. And with this improved the lift data, so now our model online CMAX predict much better results. So here is the evaluation of our online CMAX predicted hourly PM 2.5. Left is the domain average for Eastern US, because this region affected most by this fire event. We can compare our online CMAX with the operational model. So here the online CMAX is the red curve, and the blue one is our operational model. You can see our operational model. Online CMAX match this observation very well in terms of the peak value and the timing. And on the right is a so-called performance diagram. So includes three major metrics: probability of reduction and success ratio on axis, and CSI represented by this shaded area. So compare this red curve with the blue one, we can see our online CMAC has higher CSI, higher POD, indicating better performance. This is another case. Just we had for this month on July 17, further demonstrate our online CMAC predict more reasonable PM2.5 concentration during another file called the Alberta file. That's from the West Canada. The peer results from the Eastern Canada. So if you look at the left-hand side, our actual operation model over-predicted for some region. But if you look at it on the left-hand side, our model prediction match the observation much better, especially for Eastern US, even though with some of the underpredicted near the northbound compared to operation model. And so we're also interested in how model performance on the ozone prediction. We are not only interested in the PM2.5. Ozone is another important pollutant. So left showing the overlay of the operation model forecast over the Eastern US. And the coastal region, we can see our current operation model actually significantly underpredict the surface ozone. But on the left-hand side, you can see with this our using the online CMAC, our model actually capture this event very well. So the evaluation of daily 8-hour maximum ozone further demonstrates our online CMAC can capture this higher concentration. If you look at on the left-hand side, this is the performance diagram. So actually online CMAC is higher CSI, higher the POD. Sometimes maybe even for this case, for this higher value of threshold value, we can see the online CMAC even have a higher the successful ratio. So all this demonstrates our model performing pretty good for ozone episode case. So usually we only focus on the model evaluation compared on the surface. So this we think of whether how model performs vertically. So we compare our model predicted AOD with the satellite, the measurement. So left is our model predicted AOD, right is versus the measurement. So we can see actually our model can capture this the pattern and the magnitude pretty well. Summary. So NOAA has developed this online CMAC system within the UFS framework to better represent the Wi-Fi emission and to improve the prediction or impact of air quality prediction. So this online system is currently being evaluated as a candidate to replace the current forecasting system. And based on the evaluation, we can see this online CMAC show much better performance compared to the operational model for both the ozone episode and for PM2.5 prediction. Looking ahead, so we definitely are going to include the VOC emission from Wi-Fi, and we'll test the system at high resolution, and we'll update our system model and along with anthropogenesis. So we'll using the data simulation to improve the initial condition and using some of the shorter range time period training algorithm to approve the bicycle the product during the heavy fire events. That's all. Thank you so much.
Is there a question for jumping?
When will the system go online? When is the implementation?
So our original plan, so we support deliver code by the end of May, because some of the performance for this fire event we used for last year when we do lecture, we have a very few the fire to perform to evaluate model performance. But this time when we prepare to deliver the code, we get this heavy fire event, found our live data on the political emission quite significant. So next we decide to apply this scaling factor I mentioned at the beginning. So we have to redo everything. We plan to deliver code by the end of October, and the code we will implement by end of January next year.
Thank you. I think it's time to move on. Thank you, Jumping. So next one is Bo Wang.
Yeah, this is my slide. Good afternoon. My name is Bo Huang from NOAA series, CU series at NOAA GSL Lab. And today I'd like to use the opportunity to talk about our aerosol data assimilation development within JEDI for UFS model. So you can see this is a collaborative effort across universities, NOAA research labs, operational centers, GCSDA, and yes, that's all. So today I'm going to start with a quick introduction of our initial aerosol data assimilation development for GAPS aerosol model and its near real-time evaluation. Then I'm going to present our recent extension of this JEDI-based 3D MR aerosol data assimilation system for NOAA's future operational UFS aerosol model. Lastly, I'm going to highlight our ongoing collaborations to enhance this JEDI-based aerosol assimilation system. The first part of this work is funded by NOAA WPO and the CPO program, and these two projects were completed already. So the global ensemble forecast system aerosol GAPS aerosol went operational to provide global aerosol forecasting since September 2020 at NOAA. Its aerosol module is based on NASA's go-kart model with 15 aerosol tracers, including dust in 5 size bins, sea salt in 5 size bins, total organic and black carbon in 2 size bins, and also sulfate aerosols. The most common aerosol observation is a 2D column integral aerosol optical depth AOD. It represents the total extinction of solar or lunar radiation by aerosols over an atmospheric column. So the animation at the bottom shows an example of the coverage of NOAA's 550 nanometer AOD retrievals in a 6-hour data assimilation window. Currently, several operational and research communities have been running near real-time AOD assimilation for aerosol forecasting and producing aerosol reanalysis, such as ECMWF, NASA, US Navy, GMA, and recently at our lab, GSL. In our AOD assimilation, all 15 aerosol species will be used to simulate AOD, and then an AOD increment will be calculated to further adjust the aerosol species. Next one. This is the flowchart of our system. It is built upon the ensemble variational framework within JEDI. Besides that, in the ensemble forecasting step, we further scaled and stochastic perturbed aerosol emissions. It was meant to better account for the aerosol emission uncertainty and further improve the performance of the AOD assimilation. And we have this work published at GEMS. If you're interested, you may refer to this paper. And since October 2021, we have been using this system to run the near real-time VS AOD assimilation at our lab. And we have 2 parallel runs. The first one is free run without AOD assimilation. The second one is LDA. It runs 6-hour assimilation of NOAA VS 550 nanometer AOD retrievals. Again, in our ensemble forecast step, the aerosol emissions are skewed and stochastic perturbed. And also in our near real-time run, we are using the GSL's intermediate CCPP-based GAPS aerosol model, while the operational GAPS aerosol model is based on the new ops interface. But we believe that the DA impact derived from the CCPP version should apply to its new ops version as well. And we also displayed our near real-time results at the GSL website. And here we compared with AeroNet AOD, NOAA VIRS, and NASA MODIS AOD, and the near real-time AOD analysis from NASA GOES, NASA JUICE, and ECMWF CAMS model. In the interest of time, I will only show the verification against NASA's AeroNet AOD in 2 months, like December 2022 and June 2023 in the top panel and the bottom panel, respectively. And NASA's AeroNet provide very high quality AOD. It's normally used as ground truth for aerosol verification in our community. So you can see here in blue, and compared to the free run 6-hour forecast in blue, the LDA 6-hour forecast in green, and the LD analysis in red. You see the LDA has a much better agreement with AeroNet AOD compared to the free run 6-hour forecast. And recently, we extend this JEDI-based 3D MR aerosol assimilation system for NOAA's future operational UFS aerosol model. This work was funded by NOAA WPO and the GSL DDR funding, and partially by UFS R2O Advanced Compilation Project. So as you may know that, and collaborative effort has been ongoing at NOAA to planning to integrate global prediction within the UFS model. Here we call it UFS aerosols. Compared to GAPS aerosol, UFS aerosol adopts updated version of go-kart model, and a detailed comparison between the UFS aerosol model and the GAPS aerosol model was given at in my colleague's talk at AMS. So here, what matters to our AOD assimilation is that the new model will include additional natural aerosol species in 3 size bins, as shown in the animation in the bottom. And to accommodate this change, we extend the AOD forward operator and extended linear and adjunct model in JEDI UFO. It means that when we're calculating in the forward model, we will calculating the AOD. We will consider the contribution from the natural aerosol species, and in return, the resulting AOD increment will be also used to adjust the natural aerosol species as well. All the development has been merged to JEDI's internal repository, and hopefully it will eventually become public available through JEDI's future releases. Here, we run 1-month sampling experiment to evaluate this new development in October 2027. And still we have two runs, the free run and LDA. In the LDA experiment, the aerosol emissions are not skewed or perturbed yet. We are working on that. Hopefully it will be done very quickly. And the animations here compares the free run and LDA against the VRS AOD retrievals. So you can see that the LDA actually fits the VRS AOD much better, suggesting that our developments works as expected. And here we compared our UFS aerosol AOD with Aeronet AOD, the top panel. And here we also include the CCPP-based GAPS aerosol run. I mean, this is not apple-to-apple comparison between these two model run because they have different configurations, and also they are covered different, they are all October, but at different years. But consistently, we can see the LD assimilating AOD in LDA shows positive impact in both model runs. And here we also compared our UFS aerosol analysis against AOD reanalysis from NASA Mero 2 and EC's CAMS-RA. So the top panel shows the monthly average AOD in Mero 2 and CAMS-RA, and the lower two panels shows the bias of the free run 6-hour forecast and LD analysis. So you can see the LD analysis actually shows smaller bias compared to free run, except I'm not sure how to use it. Except over North Africa, you can see that LDA analysis actually shows a larger negative bias. But we found it's because we are assimilating different AOD retrievals in our analysis and also the reanalysis from NASA and E7WF. In our AOD analysis, we assimilate NOAA's VRS AOD retrievals. However, in the reanalysis from NASA and E7WF, they assimilate NASA's MODIS AOD. So as you can see in the bar plot over North Africa region, which is enclosed by this green circle, you can see the NASA's MODIS AOD is much higher than NOAA's VRS AOD. As a result, our AOD analysis is much, will have a larger negative bias when we compare with the reanalysis from NASA and E7WF. So this is also raise the uncertainty from the observation perspective in the aerosol data assimilation. And next, I'm gonna spend some time talking about our ongoing collaborations, attempting to further enhance this JEDI-based aerosol data assimilation system. As you may realize, in all the diagnostics I showed in the previous slides is all performed in terms of AOD, not specific aerosol species. It is because assimilating the integral AOD retrievals at a single wavelength is not able to properly constrain in the 3D aerosol species in the model. So as you can see here, the 3 profiles gives you can see the profiles for dust and also organic carbonaceous aerosols are very different in our analysis in red, and in NASA's reanalysis in black, and in EC's reanalysis in gray. This large uncertainty make it very difficult to understand aerosols' relative impact in the model. But we have opportunities. So in our current project, we are gonna in our upcoming project, we are gonna collaborate with aerosol experts from NASA, UMBC, and so on to assimilate NASA's next generation phase aerosol retrievals to further including multi-wavelength AOD retrievals, fine mode fraction of AOD, single scattering albedo. Simultaneously assimilating all these AOD retrievals is expected to further improve the aerosol representation in UFS aerosol model, such as aerosol composition, physical and absorption properties. And this work was is funded by NOAA CPO program. And also in most of the AOD assimilation system, they are assimilating the daytime AOD. This can be a problem, especially for the global AOD assimilation system. For example, the resulting analysis may not be able to better capture the aerosol diurnal variational features because of missing the nighttime AOD retrievals. To improve over this, we're going to collaborate with University of Iowa to assimilate nighttime AOD derived from various moonlight observations. And our preliminary results shows that assimilating complementary nighttime AOD provide additional information here. And lastly, beyond the observations, we also need to further address the inherent deficiencies in our current aerosol assimilation. Otherwise, it will not be able to make full use of the observation information here. So first, we would like to deal with the non-Gaussian of the distributions of AOD. To do this, we plan to assimilate the log transform of the AOD, which better satisfy the Gaussian assumption, Gaussian distributions, which is assumed in our current EMVAR update and the NKF update. So it should be able to further improve the AOD assimilation performance. And the second, as I mentioned earlier, our aerosol system, data assimilation system is an ensemble-based system. Even though we already perturbed aerosol emissions, however, its spread is still far from sufficient. So, okay, thank you. We're going to develop some stochastic parameterizations to further improve the ensemble spread. And lastly, we also need to address the uncertainties related to observations and also aerosol models. And all the proposed tasks here, we plan to implement them within JEDI, and hopefully they will be accepted and eventually become public available. That's my last slide. Thanks for listening.
Thank you very much. Are there any questions for both?
Well, great work. And also thank you for showing these uncertainties in the AOD data.
Yes.
We have to deal with, always we have this challenge, especially with the satellite AOD. Now, what do you think about assimilating the surface PM2.5, which can help us to improve air quality forecasting?
I mean, this is a global data assimilation. So right now, AOD is the most common observation we're going to assimilate in the global data assimilation. So I would say assimilating PM2.5 will help to further improve the model, but the data is very local, so we're not sure how it will impact in the global context. It would be, if in the region data assimilation, it should have very obvious impact, but for its impact in the global model remains to be investigated. Thank you.
Thank you. So we'll have to move on now to the next talk by Barry Baker.
Yeah, so unlike everyone else, I'm not going to talk about results right now. I'm going to be talking about a future application within the UFS. And so mainly the development of the configurable atmospheric chemistry model, and how can we use this within our future applications here. And so this is a big collaborative effort between most of the OER labs, namely ARL, CSL, and GSL, as well as engagement with NCAR and some of other labs. And forgive me if I didn't include all of the names here. There's going to be a lot more people working on this than what's listed here, so please forgive me if I didn't put your name up here. So this is just kind of a general overview of what is currently within the UFS. So we have right now mainly 3 applications that are in development, namely the RFS smoke and dust that Ravon talked about, the online CMAC that Jinping talked about, and the one that Bo just mentioned, which was the UFS aerosols. And then there's also the UFS RACMs that is not in an operational model, but is being run externally. And so we have different levels of complexity between these, anything from simple tracers to, adding in 250 tracers for regional air quality. And so, there's a large range of applications that we need to be able to cover. But right now, we actually have 3 different applications with 3 different component models within the UFS to accomplish this. And from a maintainability standpoint, this makes it very difficult. And so one of the things that we're going to try to do is to unify this into a single model so that we can, have the flexibility and the engagement to actually maintain these systems for the future. So, like I said, we want to be able to do this to be able to improve the aerosol feedbacks, to improve aerosols for wildfire smoke forecast and dust forecast, but also to improve other pollutant forecasts such as ozone and aerosols for air quality applications. This is a large collaborative effort. Right now, one of the things that we're a little bit worried about for the community is, for instance, like WRF-Chem. What is the future of WRF-Chem? Hopefully that, we have this as a replacement that the community can use, and we can really leverage that community that's out there already to further enhance this. And so the other thing is that what we want this to do is to unite across NOAA labs to actually leverage the workforce that we have to really improve and maintain these models. And so this is the overall structure of what we're thinking for CAT-CHEM. So, basically it would be a submodule of the UFS weather model. And underneath of that, there will be basically, multiple different things where we can store all of the source code, which are very simplistically wrapped Fortran routines, or, whatever language it ends up being, probably Fortran. But, and then we can also store a lot of our parameters, because we have a lot of parameters with our chemistry routines to be able to solve, the stiff chemical equations and all of the reactions that need to happen, but also aerosol properties and things like that. And then we'll have, a utility folder to support all of these infrastructure and things. And then essentially what we're envisioning is to be able to have different drivers, including CCPP or as a NUOPSI component, and possibly even future, being able to have engagement with, let's say, GFDL, and to get them to engage within the UFS in some form of matter for atmospheric chemistry. And so we've actually been having preliminary talks with them already, and hopefully we can continue to engage them. And so this is just a overview of kind of the actual complexities again. And so, within CAT-CHEM, there'll be aerosol schemes and gas phase schemes. And I think the interplay between those is really going to be the crux of the success of this. But, there's different levels of complexity to where, you can have no aerosols or no gas-based chemistry, adding in greenhouse gases or, simple tracers to, really complex chemistry, such, for aerosols, isoropia or Mozart or, things like that, or, for gas-phase chemistry, going from like carbon bond mechanisms or to even more complex mechanisms for research applications, not necessarily just for operational use. But, if we look at this to, kind of the actual operation areas, you can see that there's the level of complexity really does change throughout the system, and we have to be able to support that in a flexible and easy way. So what we're hoping for is to leverage what the land model has kind of done in that structure, is to be able to drive these things in a very simple way, but also be able to hook up through different drivers, as I mentioned. So just as a little bit more detail, this is kind of what we're envisioning for within our source. So we'll have different mechanisms and aerosols, and then the chemical solver, which would be MICM, which I'll cover in the next slide. For photolysis, we could have a couple different options, and right now we're eyeing TUVX or CloudJ. And then, of course, there's going to be online emissions. So these are things that are like dynamically produced by or weather-driven emissions, such as, biogenic, fire, dust, lightning. And we want to leverage the things that we're already doing for UFS aerosols and online CMAC within this. And then, of course, there's going to be, surface interaction. So this could be, dry and wet deposition, but also, in the future, we're hoping for bidirectional ammonia and maybe, interactions with carbon cycle and things like that. And so I don't want to necessarily go too deep into this, but just to speak a little bit more, we are collaborating with NCAR on the chemical solver. And in this case, we're going to use the model independent chemistry model, or MICM. So this is an ongoing collaboration that we're hoping to be able to start integrating this very soon. They've actually just given us the first code base to be able to start integrating. And so we're going to be looking at how to integrate that this fall. But it has a very simple way to do this. And so this is what they're going to use within CAM or impasse or CAM-CHEM. And we're hoping to be able to use this within the UFS as well. The other thing that is coming out of this project is, for all of these applications, we need a way to be able to do emissions. And so we're also developing a emission component that is based on the Harvard emission modeling component, or HEMCO, to be able to put that into the UFS and drive all of our UFS applications with a single emission processor, rather than using multiple different emission or ways to ingest data into the UFS for air composition modeling. So just to wrap up, we have our official initial code repository that is within the UFS community page. You can see the GitHub link here. And one of the things that we're hoping for is the reduction of required libraries, such as Maple, that is becoming a little bit of a sticking point for operations. But then, again, what we want to do is to unify the atmospheric composition development across the labs and within the community. And so, there's all the GitHub links for all the things. And, please, we're welcome to collaboration and talking about this. So thank you.
Thank you very much, Barry. Are there any questions for Barry?
I was wondering if you put any thought into how you're going to couple this to the physics as you grow more and more complicated with the chemistry.
Yeah, that's a very good question. It's a very not easy question, right? So it depends on, what level of interaction do you want or need, and really, do we see a benefit from that interaction, right? So, for instance, the interaction of wet deposition. So that's a really easy one, right? Not necessarily easy, but direct impact, right? So it can have, an impact on cloud formation, or even removal of those things, or, so I would say that it's definitely something that we're really interested in. And one of the reasons why we're going down the CCP route to begin with is so that the interaction with physics can happen in a more organic way than what it is right now.
Thank you. I think it's time to move on. So the last talk of the session is by Laurie Prowiler.
Okay. Got it. Okay, thanks. Okay, so I'm going to talk about a little bit different of an application for the UFS, and that is greenhouse gas data assimilation. And we also want to estimate fluxes. So that's why the flux inversion part is also on there. This is work being done by myself at the Global Monitoring Laboratory and my colleague Andrew Hsu at Colorado State. So in this talk, I'm going to tell you what we're trying to do, why we want to do it, why we want to use the UFS, and then finally, a major roadblock we're currently encountering. So the idea will look familiar to you weather people. The idea is that you make a prediction of the greenhouse gas in the atmosphere. You bring in the data, and in our case, we want to adjust the state and the forcing, which is the emissions. And so our products are a carbon analysis and also the estimated fluxes. I want to give you a little bit of background on why we want to do this. And this projector is wreaking havoc with my beautiful color schemes, unfortunately. But I want to show you the situation where we find ourselves in with respect to the Earth's energy budget. This figure is based in part on measurements that we take at my lab, and it shows the contributions of different greenhouse gases to the radiative forcing. And you can see that CO2 is rapidly climbing, and it comprises most of the direct radiative forcing. Methane is number 2. Now, if we want to understand the temperature effects of these gases over time, we have to use a climate chemistry model. And if you look at the recent IPCC report, you see that CO2 could have supplied about 3/4 of a degree, methane 1/2 degree. The reason why it's so much larger than you would expect from the direct radiative forcing, of course, is because there's chemistry and this affects other radiative forcers. But what I want you to look at is the uncertainty ranges. These are model ranges from the IPCC ensemble. And what this tells us is that we don't know very well how to understand the budgets of these gases. There's a lot of uncertainty in feedbacks. There's uncertainty in the chemistry. And so by doing these reanalyses of greenhouse gas budgets over time, we can hope to improve our understanding of the budgets, improve the models we're using to make predictions of the future climate. So as an example, I just want to bring up quickly carbon climate feedbacks. These are not very well understood. A big one, of course, is what's happening in the Arctic as the Arctic warms. Carbon may be mobilized to the atmosphere. It could be that the amount that comes out is about 4 times what we've already emitted since pre-industrial times. By doing these retrospective analyses of the carbon, of the CO2 and methane budgets, we can hope to understand these feedbacks and maybe perhaps predict them. So right now, before I start, one more background slide, and that is on the policy side. We know that countries are required to come up with 5-year plans for reducing emissions. How do we verify these? One way we can verify these is by running these atmospheric data assimilation systems and verifying that emissions are going in the direction we want. In the US here, there's a lot of attention to methane. The White House is very interested in tracking methane emissions and understanding whether our bottom-up ideas of what's being emitted agree with what we measure in the atmosphere. Okay, so this is an example result from our current system, Carbon Tracker Methane. And I won't go into what the figure on the upper right is, but the bottom left is showing you an example product from this. You can see for North America, if you look at the orange bars, that's oil and gas emissions and coal also. You can see that these kind of emissions were rising up until sometime between 2010 and 2015, and they've started to drop recently, perhaps because there's been more attention on fixing leaks from oil and gas, maybe reduce coal usage. So this is the sort of picture we can get from these systems. And before I go any further, I want to point out that when I'm talking about CO2 simulations in the UFS, I am not talking about the climatology that interacts with the radiation. I'm running these things as passive tracers. Down the road, we could have interactive greenhouse gases, but that's pretty far down the road. So why do we want to use the UFS? First of all, we're limited in our current system to what spatial and temporal resolution we can go to. We're limited to 1 degree. If we want to resolve emissions at finer spatial scales, we need a more state-of-the-art model. Not only that, but our current system uses a European chemical transport model driven by ECMWF winds. We would really like to use a NOAA product. And there's other attractive things, such as the GEFS reanalysis ensemble. We might be able to use this to estimate our model transport error, which is part of what goes into data assimilation systems. And then there's linkages between the carbon moisture budgets and the hydrological cycle. If we could actually get a land surface model that could predict carbon as well as moisture that could be advantageous. So these are some of the reasons why we want to try to use the GFS. And now I'm going to talk about where we are right now. For us, mass conservation is a big deal. The measurements we're using are with respect to dry air mass, not total air mass. And if we get small problems with air mass, dry air mass, well, these add up to aliasing into the methane sources and sinks. And so recently we ran what I'd like to call the SHU experiment, which is a constant CO2 field. Here I've used 400 ppm, and you turn off all the sources and the sinks, you make sure there's no deposition, et cetera. And we ran this forward for about 6 days. And what you can see in the figure here is that the mass drops from something that is reasonable. It loses over, about 250 ppm in 6 days. I got curious about how this could happen. So I just went into the suite file and started commenting out, some of the physics. And it turns out that if you don't call the shallow and deep convection, you conserve global CO2 mass. So clearly, it looks like there's some kind of problem in the convection, I would say. There's other reasons why we might not conserve tracer mass, such as analysis shocks. When we bring in a new analysis, maybe there's been a jump, but these we'll deal with down the road. Now, the mass problem isn't limited to the global amount of carbon. It also affects the spatial gradients. And so on the right is the SHU experiment results, and the color bar is telling you the departure from what the expected value is, which is 400 ppm. And you can see that there's extremely large gradients. There's some holes that are almost 400 ppm. And also there's some maxima over, like, say, you can see in this picture, temperate North America. If I turn off the convection again, then I get something that we could probably work with, a few tenths of a ppm in terms of non-gradient conservation. So we know from other models that this sort of problem can be resolved. This is the model that Andrew Hsu has worked with called OLAM. And here they paid a lot of attention to the issue of tracer mass conservation, and they were able to get these gradient errors down pretty far. I mean, this is really great. So the point is, though, that we know that this kind of improvement can be done. So in conclusion, we can't really go forward until we are able to come to some sort of fix for the convection, or what appears to be a convection-related problem. Maybe it's not. It could be the clipping in the microphysics, for example. I think it's certainly is possible that this problem exists for other species like aerosols. Maybe people want to repeat this experiment and see if they can verify our results. And I also forgot to mention that I also tried the version 16 CCP physics that Kate Zhang had done a lot of hard work on to make sure that the transport was done correctly for the tracers, but that appears not to have resolved the problem. But I did want to call out Kate because she's helped us greenhouse gas people a lot, and she's, tried to help us go forward. I think probably we need to pay attention to the water budget in more detail. And I also wonder if there are problems in the water, could we actually improve predictions? This is not my area, so I'm just speculating here. So that's what I have to say, and I'm happy to answer questions.
Thank you. Thank you. Penguin.
Yeah, as we discussed, I hope you can use our latest version of the physics. This problem I hope it will go away, and we did work a lot on this negative tracers, not only in the convection, also in PBR scheme. Andrew, I have a question. I've been looking around all around the world to find the CO2 climatology extends to the vessel paths with the vertical, not constant CO2 concentration. I couldn't find it. Hopefully in the future, maybe your project can provide this. We know the CO2 changes reduce not as from the upper stratosphere to mesosphere, but because the lack of data set, we have to use constant.
Yeah, I mean, I don't know too much about what's happening up in the upper atmosphere with CO2, but I could look into that for you. And Andrew and I will be happy to test drive your new version of the physics, and I will let you know what we find. Hopefully it will be good news. That'd be great.
Sometime we'll talk more.
Thank you.
Laurie, yeah, it's a very interesting finding and very important. Now, in your version in this model, is CO2 affected by the convection scheme at all? Those tracers?
No, it's a completely passive tracer, and it is not the same thing as a CO2 that does feedback into the physics. This is totally separate from that. Would I like to have CO2 interactive? Absolutely, it'd be fascinating, but not right now.
Yeah, because that's okay.
I think this was an earlier version of the physics that had some errors in the transport that were then corrected. Is there another question?
These calculations were done with version 17 P8.
The updates were made after, I think, P8. Well, most recently.
Right, I'll check out that code and use it.
Thank you. Is there another question for Laurie, or we had a question earlier that somebody wanted to ask Jianping still? Brian, did you have a question for Jianping? Where was it? Bo, okay. Is Bo still here? Okay.
Ravon asked you about incorporating surface PM into your data assimilation framework. And I was wondering if you're thinking about in the future, potentially aerosol layer height products that might be available from satellites along with aerosol optical depth as well.
Yeah, actually, we will think about assimilating like aerosol height retrieval, product from the satellite, but we are not sure like the quality of that retrieval is. If it's very high quality, we would be able to assimilate it, but we are not sure the quality of the retrieval yet. That's the plan. We indeed plan to assimilate the aerosol height. Still depends on the quality.
I think, for example, C1 Lang used a type of aerosol air plume rise from wildfires and was able to see some issues there. So I think there's a lot of problems there, even if it's not there right now for you to use.
Yeah, indeed, kind of like at the pace, they also have the aerosol height retrievals. I think we need to talk with like the aerosol experts from NASA and to see how we can assimilate that retrieval as well.
Okay.
Thank you.
Thank you so much for this very brief, very interesting and engaging session. I'd like to thank all the speakers again. And we are off to a break. I guess they're gonna merge all the rooms again into the plenary after the short break. So thank you so much for being here.